Hello students, welcome to the physics class. Okay, we have already studied about the concept of cells. Okay, cells are nothing but some electronic devices. About that we have studied in detail. As you know, cells are nothing but they will give us some potential difference. Which type of potential difference? Constant potential difference to maintain a steady current in any circuit. That is the device which is called as a cells. So we have studied in detail about the cells. We have studied what are the properties cells will be having. Means cells will be having EMF, internal resistance, terminal potential difference, and how will be the symbol of cell. All the things we have studied. And also we have studied cells can be combined. Means we have studied about combination of cells. Means as resistors, cell can also combine series and in a parallel manner. Okay, and also we have studied what happens to the current in of series combination of cell and what will be the current of a parallel combination of cells we have studied. Okay, so now in today's class I am going to discuss about effective EMF and effective internal resistance of combination of cells. Means you know series combination of cells means what? Like means if cell is like this, it will be having two terminals, positive terminal, negative terminal. So if negative terminal of one cell is connected to the positive terminal of another cell, again negative terminal of one cell is connected to positive terminal of another cell. So like this, if you are going to combine the cells, this combination is called as a series combination. Okay, and also if you want to combine the cells in a parallel manner, means they should be connected between the two common points. Means if you have the two common points A and B, so you are going to connect the cells like this. Like this you can combine them. So this is what a series combination of cells and this is parallel combination of cells. So in the last classes we have discussed about what will be the amount of current for series combination and amount of current for parallel combination we have studied. As you know, the cell will be having EMF, internal resistance and terminal potential difference. So here if you are combining two or more cells in a series pattern, they will be having individual EMFs also, like it will be having E1, E2, E3, E4, like that. Individual EMFs will be there. Na? For every cell it will be having its own EMF and also it will be having internal resistance. Okay, and as you know from the concept of resistors only we are thinking about effective resistance or effective internal resistance or effective EMF. That means what? Instead of the combination we can use only a single cell, which will be having a effective EMF, E effective, or you can say this effective cell can have effective internal resistance also, R effective. Yes or no? Means instead of using two or more cells we can use or we can replace this combination by single cells, and that single cells also will be having effective EMF and effective internal resistance. Yes or no? So in this class, in today's class, we are going to determine one expression for effective EMF and effective internal resistance for combination of the cells. Okay, so here for the series combination we will be having ES, means effective EMF of the series combination of the cells. Similarly EP for parallel combination, effective EMF of parallel combination of cells. Similarly for the internal resistance RS and RP, effective internal resistance of series combination, effective internal resistance of parallel combination. So here we are going to determine expressions for ES and RS for series combination, EP and RP for parallel combination. Okay, so now let's start with the series combination first. Okay, we start with the series combination, or you can give the heading as expression for effective EMF and effective internal resistance for series combination of cells. Okay, so now first think about series combination of cells. So here I am going to consider two cells which are combined in the series pattern. See here how to combine the cells in series. See here, this is one cell, this is one cell, and this is another cell. So these two cells are combined in series pattern, and the first cell is located between the points A and B, and the second cell is located between the points B and C you consider. Okay, now this first cell I will call it as P and the second cell B Q. Okay, so this cell P is having EMF E1 and the cell Q is having EMF E2. So E1 and E2 are the EMFs of the cells P and Q respectively. Next, R1 is the internal resistance of the cell P and R2 is the internal resistance of the cell Q. So R1 and R2 are the internal resistances of the cells P and Q respectively. Okay, now in this combination the current sent by these two cells be I. I is the current sent by these two cells. As you know clearly, in series combination two things are meant to get important. What is means? In series combination I is same throughout. It may be combination of resistors or it may be combination of cells, but the current will be same throughout, but the potential difference is different, because in series combination we will be having end points for every current element. It may be in the combination of resistors or it may be in the combination of cells. We will be having two different points, two different end points. With respect to them, we will be having different potential differences. That's why we will be different and I will be same in the series combination. So here in our given diagram, I is the current sent by these two cells. Okay. So now I is same, don't worry about that. But what about V? What about potential difference? Okay. So here I am considering VAB. VAB is the potential difference of this cell. VAB is the potential difference of this cell between the points A and B. So VAB is the potential difference between A and B. Next, VBC. VBC is the potential difference between the points B and C. And also we are having A and C. Hence VAC is the potential difference between the points A and C. Understood? These are the three different potential difference of this combination. Okay. So this is about how we have analyzed the series combination of the cells. Okay. Now let's continue. So while we are discussing about cells, the concept of cells, we have derived one relation which gives us the one expression we have derived that gives us the relation between terminal potential difference V and EMF of the cell E. Try to remember the expression. That expression was V is equal to E minus IR. So this was the relation between EMF E and terminal potential difference V, where I is the current and R is the internal resistance. So this expression we are going to use. So by the relation between terminal potential difference and EMF, we have V is equal to E minus IR. So call this as equation number 1. Okay, now see here. Now apply this equation, means by applying this equation, let's calculate the potential difference between the points A and B. The potential difference between the points A and B is, as I told you, it is VAB. Now what is E? E1, I, R1. So can I write the potential difference between the points A and B as E1 minus I, R1? Yes or no? See here, between A and B we are having E1 and R1. Applying this equation here, VAB is equal to E1 minus I, R1. Call this as equation number 2. Now, what is the potential difference between the points B and C? VBC is equal to E2 minus I, R2. I is same, hence it is E2 minus I, R2. Call this as equation number 3. Now, what is the potential difference between the points A and C? What is the potential difference between the points A and C? Can we write it as the combination of this and this? Means VAC equal to VAB plus VBC. Yes or no? The potential difference between the points A and C is nothing but the combination of potential difference between A and B and potential difference between B and C. Hence we can write VAC is equal to VAB plus VBC. Now in this expression, what I am going to do is, in this expression you just substitute the values of VAB and VBC. See here what we have, VAC equal to VAB. It is E1 minus I, R1 plus VBC. I write it in the bracket. Here VBC is there. VBC is E2 minus I, R2. Okay. Now just open the bracket and rearrange the terms. What we have, E1 minus I, R1 plus E2 minus I, R2. Okay. Now how I am going to adjust the terms, you see. E1 plus E2, I will write, means these two terms, E1 plus E2. Okay. So next what we are remaining with? We are remaining with I, R1 and I, R2. Take minus I common. Minus I common, R1 plus R2. Okay. Call this as equation number 4. Okay. Now up to here you stop it. Now this combination, what I am doing, I am replacing this combination by one effective cell. Means here we are having two cells, P and Q. Instead of using P and Q two cells, can you use a single cell which will give the same effect as that of these two cells? Yes or no? That only we can call it as a effective cell. So instead of using these two, I will use a single cell. Single cells, what is their single cell? Between the points A and B, one single cell I will use. And that is called as effective cell. And that effective cell will be having one EMF and that will be having one internal resistance also. but EMF of that effective cell is effective EMF, and internal resistance of that effective cell is effective internal resistance. So how can we write that? ES and RS. Yes or no? So here you can write, for that diagram you can write V is equal to, what we can write? VAC only, na? Because here we are using these two cells between the points A and C. So that effective cell also should be between the points A and C, na? So here we are having them between A and C. So can we write VAC is equal to ES minus IRS, because you know the relation is V is equal to E minus IR. Hence here we are using the effective EMF and effective internal resistance ES minus IRS. Call this as equation number 5. Now compare these two equations 4 and 5. Compare. VAC is same, VAC is same. Okay. ES is there, E1 plus E2 is there. I is same, I is same, I is same. RS is there. Here R1 plus R2 is there. So what we can conclude by this two equations? ES equal to E1 plus E2 and RS equal to R1 plus R2. So I will write that ES equal to E1 plus E2 and RS equal to R1 plus R2. Okay, so this is the expression for effective EMF of the cells in series. This is the expression for effective internal resistance of the cells in series. Understood? What we done here? We taken two cells P and Q of EMF E1 and E2. Two cells P and Q of internal resistance R1 and R2. We have combined them in series, and P is located between the points A and B. Q is located between the points B and C, and I is the current sent by those two cells. And we are considering the potential difference between A and B is VAB, potential difference between B and C is VBC, potential difference between A and C is VAC. And now we are considering the relation between terminal potential difference and EMF of the cell, that is nothing but V is equal to E minus IR. With respect to that, we are calculating VAB, VBC and VAC. VAB is nothing but I minus E1 minus IR1, VBC is E2 minus IR2. And VAC is combination of these two, VAB plus VBC. We are substituting the terms and comparing and considering one more effective cell here. Instead of these two cells, we are using a single cell with effective EMF and with effective internal resistance, and for that we are writing the expression. Then by comparing these two, we will get ES as this much, RS as this much. So understood? This is about series combination of cells. So this question is very important. As you know already, I have told you this question is asked for last two question paper. Okay. Now what happens to the EMF of the cell, means effective EMF and effective internal resistance when the cells are combined in a parallel manner. So what happens in the parallel manner? So this is one cell. This is one more cell. So there we got again two cells P and which are combined in a parallel manner. Okay, so now these two cells are combined between two common points, that is A and B. And here, as you know, in the parallel combination, potential difference will be same. Means potential difference is only one, that is VAB. We have only one potential difference, that is VAB, because it is only between the points A and B. But the current is different. Here main current is I, but by this cell P the current sent is I1. By the cell Q the current sent is I2. Understood? And as usually the E1 and E2 are the EMFs of the two cells P and Q, and R1 and R2 are the internal resistance of the cells P and Q. And I1 and I2 are the current sent by P and Q. VAB is the potential difference between the points A and B. Okay. Now again you apply the relation between apply the relation between EMF and terminal potential difference, that is V is equal to E minus IR. Call this as again equation number 1. Okay. Now for this cell P, you apply this equation. What happens? VAB is equal to E1 minus IR1. I am just adjusting the terms. So I1 R1 it is, because we are having I1 and I2 are different. VAB is equal to, instead of VAB, if you call it as only V also, no problem, because you are having a single potential difference there. So VAB or V is equal to E1 minus IR1. Okay, I am just doing some simple adjustments. I1 R1 equal to E1 minus VAB. Okay. So here we are having I1 R1 equal to E1 minus VAB. I am writing I1 equal to E1 minus VAB divided by R1, and call this as equation number 2. I have just adjusted the terms over there. I1 R1 is equal to E1 minus VAB, and taking this R1 to this side. So this is equation number 2. Same, this expression you apply for this cell also. So what happens when you apply to this cell? See here, VAB equal to E2 minus I2 R2. E2 minus I2 R2. So I am applying this for this condition for the cell Q. Okay, now I2 R2 equal to E2 minus VAB, and same I2 equal to E2 minus VAB divided by R2. Call this as equation number 3. And I have given the expressions for the branch currents I1 and I2, and you know already that this current I means the current of the combination of these two cells. I is what? The current of the combination of these two cells. Current given by both P and Q. But individually current given by P is I1, current given by Q is I2. So you can combine them as I is equal to I1 plus I2. Yes or no? Branch currents are nothing, main current is nothing but sum of branch currents. That's why you can write like this. Now you substitute the values for I1 and I2 over there. So I is equal to I1 is nothing but what? E1 minus VAB divided by R1 plus E2 minus VAB divided by R2. Now take the LCMs. I is equal to, LCM is R1 R2, E1 R2 minus VAB R2 plus E2 R1 minus VAB R1 whole divided by R1 and R2. So now what I am doing, I am just taking this R1 R2 to this side. So what that equation becomes, I into R1 R2 is equal to this whole term. Okay. Now how we can write this expression? See, I R1 R2 equal to E1 term is there, E2 term is there. You cannot take anything common here. So write it as it is. E1 R2 plus E2 R1. E1 R2 plus E2 R1, and VAB is common here. Minus VAB. So take it common. Minus VAB into R1 plus R2. Yes. Minus VAB into in bracket you take R1 plus R2 is remaining. Okay. Now send this whole term to this side. This VAB is there, na? Send that to this side and send this to that side, because we have to form the equation in the form E minus IR. But here what we have, I is equal to E minus V we have, na? That's why you can use it as you can just exchange the terms like VAB into R1 plus R2 is equal to E1 R2 plus E2 R1. Take this I term to that side, minus I R1 R2. Okay. What is that? Means don't get much confused, because only I am just adjusting the terms. Let's look at the terms carefully, that much. So what I am doing again here, send this R1 and R2 to this side. So what happens? VAB is equal to E1 R2 plus E2 R1. E1 R2 plus E2 R1 divided by R1 plus R2, because I am sending R1 and R2 to this side, minus I R1 R2 divided by R1 plus R2. Let's give a whole bracket here. So is it in the form V is equal to E minus IR? V is equal to E minus IR. Okay. Call this as equation number how much? 4. Now what we have to do? We have to use one effective cell. Means instead of these two cells in parallel, let's use one single cell. Single cell means how it will be from the point A, and we don't have any point C here, so it is just B. So a single cell between the points A and B. So it will be having effective EMF EP, because we are replacing this single cell in the parallel combination. So hence it is EP and RP. And the current is same, I, potential difference is same, AB. So now for this combination you write this expression, V is equal to E minus IR. How it will be? V AB is equal to E minus IR is there, na? So EP minus IRP. So this expression is for this combination. Call this as equation number 5. Now what we have to do now? Compare these two equations, 4 and 5. Compare. What happens here? VAB is same? Same. Okay. Now, instead of EP, you have one whole term here. So, EP is equal to P1 R2 plus P2 R1 divided by R1 plus R2. So, in the place of EP, we have this minus I same. In the place of RP, we have this. So, what is RP? R1 R2 divided by R1 plus R2. So, we have got two expressions. By this derivation, we have got two expressions. First one is what? Effective EMF, and it is effective internal resistance. Okay, let me revise this once again. What we done here, we have considered two cells P and Q combined in a parallel pattern. These two cells are having EMFs E1 and E2, internal resistance R1 and R2. Okay, and hence it is a parallel combination. They have different currents. P is having a current I1, Q is having a current I2, but the combination will send the current I. They are located between the points A and B, that much. Hence the potential difference is same, as they have same endpoint. Potential difference is just VAB. Okay, now apply the relation between EMF and terminal potential difference, that is V is equal to E minus IR. Now applying this condition for the first cell P, apply this condition, that is VAB is equal to E1 minus I1 R1. By just adjusting the terms, we got the expression for I1. Again, apply this condition for the cell Q, second cell, that is VAB is equal to E2 minus I2 R2. See here, by adjusting the terms, we got I2. And as you know, the main current is combination of branch currents I1 and I2. We have just added, we have taken LCM. This R1, R2 have applied, I have sent it to this side. Now combining the terms, taking minus VAB common, R1 plus R2, and sending this VAB to this side, sending I to this side, because we want the expression in the form of this V is equal to E minus IR. Now this R1 and R2 also I am sending this side, because in this equation I have single V, don't have any extra term there. That's why this R1 and R2 also, R1 plus R2 also I am sending to this side. So it comes here. Here it is multiplying. It comes to the denominator. It comes as a dividing factor. So VAB is equal to this much we got. Now what we are doing? We are considering, we are replacing this parallel combination by a single cell of EMF, EP and internal resistance RP between the points A and B. So for this combination, I have an expression as VAB is equal to EP minus I RP. By combining these two, we got the expressions for effective EMF and effective internal resistance for the parallel combination. Sorry, it was parallel combination. Okay, so hence we have got the expressions for internal resistance, effective internal resistance and effective EMF for both series combination and parallel combination. This question was also very important, 5 marks carrying question. So nothing is there, easy. You just watch the video properly and practice it, because it's a lengthy derivation is there. So you have to practice it, then only it will be perfect for you. Okay, thank you.